Hello, my name is Sebastian Echeverria, and today I'm going to be talking about Kalki Plus, our scalable and extensible IoT security platform. In the last few years, more and more vulnerabilities and exploits of IoT devices have been showing up in the news. Because IoT devices are very prevalent, are usually not very heavily secured, and may be connected to critical networks, they are a very tempting target for bad actors. Having a commodity IoT device is something that companies may want to do to quickly enhance their capabilities with the newest technologies. If an attacker discovers a new vulnerability in an IoT device connected to a network, it can find a way to exploit this vulnerability remotely. A commodity off-the-shelf device may also have been already compromised at some point during the supply chain. For example, malware could be inserted into the firmware at manufacturing time. The attacker may then gain access to a network, which would allow them to do all sorts of damage, send fake data, disrupt service availability, gain access to internet networks, and more. Existing solutions that can be used to handle some of these issues include firewalls, intruder prevention systems, and AI-enabled traffic profilers. Some of these systems are usually fairly static with respect to the types of policies that can be applied, and they usually do not take into account the characteristics of a specific device, but rather take a more generic approach. They are also usually limited in the ways they can adapt to different threat levels that may be occurring on networks, and do not leverage environment information that is sensed by the devices themselves. Those systems that use machine learning need substantial amounts of data to be trained, and usually require connectivity to the cloud as well to work. To analyze this situation, we defined a threat model using the cyber kill chain methodology, focusing on what Paris calls the IoT-oriented cloud networks and platforms layer. We then created an attack tree to list the main threats we identified. As you can see here, some of the major threats we look into include attempts to change the security policy definitions, intercepting and changing policy-related messages in transit, and loading malware into a connected IoT device. We later used this model to guide our work, both our first attempt and our improved solution. In our previous work called Kalki, we created a platform that allows the integration of untrusted IoT devices and is able to dynamically adapt to threats it can detect. The Kalki platform has a flexible way to define states and actions, and it can react to threats using network and environment information. It also deploys different network defenses for each device and each security state they are in, using something we call micro-boxes, which encapsulate network functionality, which could be an IPS system like Snort or a proxy, for example. Each of these pieces of functionality can be passive, monitoring and generating alerts only, or active, blocking part of the traffic, sending fake replies, or so forth. Kalki is also highly configurable in order to handle vulnerabilities specific for each device model. The Kalki platform is composed of two main nodes, a control node and a data node. The control node stores policies and current state and decides when to change states and defenses based on alerts. The data node acts as a gateway which deploys micro-boxes for each device and routes traffic to them. Each IoT device connected to the platform senses or controls a set of environment variables. The network traffic to and from each of these devices is tunneled through one or more micro-boxes, which implement the network defense for that device's current security state, and which may send network alerts to the controller. The IoT controller maintains a shared state composed of all the environment variables sensed by all IoT devices, which may trigger device-related alerts. These alerts, plus network alerts that have been sent by the microinboxes, let the system define the current security states for each device, which can be normal, suspicious, or under attack. Policies in the controller can define security changes based on the device and the network alerts that are received, and may result in the deployment of new microinboxes to change the system security posture. The controller can react to both network and physical attacks. For example, it could detect brute force attacks or changes to the expected temperature ranges of a set of temperature sensors. However, after analyzing the Kalki platform, we realized it had several shortcomings. In terms of performance, the reaction time and resources needed were too high for what we wanted to achieve to prevent potential attacks. In terms of hardware, we had built this platform to work on commodity servers, but during test runs, we realized that allowing it to work on more constrained servers would help substantially in increasing the use cases where the platform could be installed. Though the policies used by the system were flexible and secured, the process needed to add or modify them was too heavyweight, requiring code updates after each change. Similarly, the rules that define when an alert from a device should be raised required code changes and knowledge of the internals of the system. This also made it harder to add new device types. Finally, adding a new device type requires implementing its API to obtain the values it can sense. However, in our past experiments, this would be the largest bottleneck in terms of the time needed to incorporate a new device type into the system. This is in part due to the changes requiring full understanding of the device interface component of Kalki before being able to add a new one. To improve this, we created a new version of the platform called Kalki Plus with the major changes to address the limitations we just mentioned. The main goals of this improved version of the platform are to improve performance and scalability, to allow the system to work in more constrained hardware, to improve the usability of both policy creation and alert rule configuration, and to simplify the process of adding new device types to reduce the time needed for this. In terms of performance and scalability, we first worked on finding a way to preload the virtual machine-based microinboxes that we used in the original Kalki platform, but then we decided that the gains from this would not be enough. The main benefit of using virtual machines for the microinboxes was to support network tools on different operating systems. But we realized during trials that this wasn't a major requirement for the people that were interested in using our system. We decided then to migrate to Docker containers, which would limit the flexibility in terms of supported operating systems, but that would allow us to substantially improve performance and scalability. We migrated the software components in the control and data node that handle the microinboxes to work with Docker containers instead of virtual machines. And we also migrated our current set of microinboxes from virtual machines to containers. We also created a simple and almost fully automated process that makes it very quick to package and create new container-based microinboxes for new network functionality that we may want to add to a deployment. When working with potential users of the system, we also realized that being able to work on a small form factor server would greatly improve the use cases where Kalki could be deployed. For Kalki Plus, we made several changes to allow it to run on more constrained computers, such as on a Raspberry Pi, and also to allow it to work on different deployment scenarios without always having a separate control and data node or having multiple data nodes associated to a control node. The move to containers helped simplify this process as the resources needed to store and run microinboxes were reduced. We also restructured some internal connections of the system to make it more flexible, allowing, for example, for one dashboard, which is the user interface we use to control the system, to control multiple remote data nodes, as well as allowing multiple deployment configurations. We also Dockerized the full platform, so setup would be easier and so it could be independent of whatever hardware we are trying to install this on. Regarding policies, we had originally created a method through which they could be defined in an external visual tool, but would then be transformed into code that would have to be integrated into our system. This was done to isolate the policy code in order to make it easier to secure and to protect. But we realized that it constrained customization and configuration too much. In Kalki Plus, in this new version, we moved the policies to the database and focused on protecting the database itself instead. We also added an integrated graphical user interface to our dashboard that is shown here that allows users to visually see and create policies. Finally, we also added support for policies that can mix device alerts with network alerts for more complex policies. The conditions from sensed values from devices that trigger alerts were hard-coded in our initial version of the system, even though the thresholds were configurable. This not only made it hard to tweak or add new alerts, but it also meant that it took longer to incorporate a new device type into the system, as code for each specific alert of the new device would be needed. In Kalki Plus, we modified the device alert handling system to be generic and moved the definition of all conditions into the database, also updating the dashboard UI to allow for the creation of alerts and the configuration of them as well. This adds a lot of flexibility when wanting to adapt the system to specific environments that may need slight customized alerts. Finally, the largest part of the effort required when adding a new device type to the system is implementing its API in code to be able to get values from its sensors. To reduce this time, we created a system of plugins where minimal code has to be written on top of an existing framework in order to implement the API of a new device type. This substantially reduces the effort of implementing these APIs, as well as the amount of knowledge of the interface component that a developer needs to create a plugin. Our experiment setup was similar to the one from our previous platform in order to get a direct comparison of its behavior. We worked with 4 representative device types that we had integrated into our system, each having specific policies and microboxes with functionality appropriate for their policies. We ran these experiments for Kalki Plus on the same commodity servers that we use for Kalki and in an isolated network. For performance, we measured the time between the start of a potential threat attack and the system changing its full security posture. For scalability, we stress tested the system to see its ability to handle multiple microboxes, simulating multiple devices being connected and working at the same time. We also started running similar experiments on a Raspberry Pi, but we have not completed them yet, and thus the results are not included here. The performance results show that on average, the first version of the system takes 29 seconds to react to threats. This is the original platform Kalki. And most of the time is preparing the virtual machine for a microinbox, which is cold booted. As expected, Kalki Plus, the new version, which uses Docker containers for the microinboxes, is much faster, with reaction times being around an order of magnitude less, while providing the same functionality. For scalability, we tested the system by incrementing the amount of microinboxes running in the background in each experiment and measuring the effect of starting a new one with this load. These charts are similar in shape, though not in scale, with the response time being a bit more stable on Kalki Plus. The scalability results show an improvement close to an order of magnitude in response time and even greater in terms of memory usage. This also means that a substantially higher amount of devices can be connected to the new version of the platform at the same time. Also, this implies that with Kalki Plus, a substantial amount of devices can be connected at the same time when using a more resource-constrained server, like a Raspberry Pi. So we have presented here our much improved version of our original security platform, now called Kalki Plus. I also wanted to mention that we have open sourced our code, and it's available in the GitHub repository shown here. In terms of future work, we want to complete the experiments in resource-constrained hardware, as well as try out different node deployments that can maintain security while adding deployment flexibility, like having multiple data nodes connected to a control node or combining them both into one single node. We would also like to have a registry to simplify the process of deploying and updating micro mboxes to deployments of our platform. That was my presentation. Thank you very much for listening.